this video on chapter 7.3.1. We're in our nuclear and particle physics unit, and this time we're looking at the structure of the atom. So the learning objective for this particular video is to describe the Rutherford Geiger Marsden experiment and interpret its results. So first off, at this particular point in history, which was around the early 1900s, so we're looking at somewhere around, probably around 1910 or so. Okay, there's a few more specific years and dates in the textbook that you'll find, but roughly around 1910, plus or minus a few years. So Niels Bohr, at this point, had come up with this model of the atom. And what happened was there was another physicist, J.J. Thomson, who was trying to come up with a theory and a model for what exactly did the center or what was the structure of the atom like, okay, as our topic here indicates. Okay, what was that structure like? So J.J. Thomson proposed what was called the plum pudding model. And the idea here was that within the plum pudding, there would be a massive ball of positive charge, and there would be sort of like a pizza where like pepperoni and cheese is scattered around. So negative electrons are roughly sort of very randomly distributed, but in a sort of even way as well. And so overall, they did recognize at this point that the atom itself was neutrally charged. And so J.J. Thomson's model was trying to explain that, but they had also discovered things like the electron by this time. So they knew there were some charged particles, and they also knew there was, because it was neutral, that there had to be a positive charge somewhere within the structure of the atom. Rutherford, as we will discover, came up with what was called the planetary model, where there was this object in the middle, kind of like our sun, and then there would be these planets that orbit around it. And as we know today, Rutherford was the sort of correct scientist in that the experiment showed that his model ended up being the correct one, or he had to come up with a model to explain things in that particular way. Okay, so in terms of the plum pudding model, this is what's interesting about it is they were able to identify alpha particles at this particular point in time. So I'm going to use a darker green to represent alpha particles. So they were able to direct alpha particles into a particular object. And we'll look at what's called the gold foil experiment a little bit later. And this is what they were trying to prove was, if J.J. Thomson's model was correct, the alpha particles would essentially flow completely sort of through the structure of the atom. Because it was neutrally charged, it would not deflect anything, okay? So because both positive and negative charge are evenly distributed. So essentially, it makes the entire thing neutral, right? So if it's neutral, and remember, an alpha particle is +2. So a +2 object passing through something that is neutral would essentially have no effect on it. So what happened was that in order to test the plum pudding model, they set up what is now commonly called the gold foil experiment, or we can credit that to Rutherford, or if you really want to credit all the scientists who were actually involved, Rutherford was probably the big guy on top that kind of helped oversee everything, along with Hans Geiger and Marsden, who was a graduate student at that time, undergraduate student at the time. So what they had set up was an alpha particle emitting station. Okay, so alpha particles are being emitted through here. In the middle, they had a thin sheet of gold. Okay, and they wanted a thin sheet of an object. Gold was particularly ideal because you can flatten it and you can make it really, really thin. Okay, so you can make it flat, make it really thin so that you wouldn't get too many particles of gold. Okay, so that was the beauty of gold. So we're looking at a gold foil, right? We're not talking about a chunk of gold. We're talking about a really, really thin paper thin like sheet of gold. And so what they saw was that most of the particles actually passed straight through. And that was starting to suggest that the plum pudding model was correct, right? Exactly what we saw here, right? So that the alpha particle should pass directly through because it was neutral. Now, here is where things get interesting. What they also were able to observe when they put um, a detector, it was a fluorescent screen essentially. So a fluorescent screen, FLU, sorry, fluorescent. Oops, I think I got an extra E there. Not very good at spelling today. Fluorescent. Okay, a fluorescent screen. There we go. Okay, so the fluorescent screen allowed for the detection of these alpha particles. Um, and what they were able to detect on this particular screen was that they detected hits. Not very often. It was more like 1 in 8,000 alpha particles where they actually did detect a hit. And the most significant ones is actually, I'm going to use a completely different color. These were actually the most significant ones. And why is this significant, you might ask? And the reason significant, how? Okay, let's try that again. Significant. So why is this so significant? Um, this essentially suggests that the alpha particles were being reflected backwards. And if we think about the alpha particle, which is a +2 charge, the only thing that could reflect it with that type of complete rebound, right, to completely almost rebound it backwards, is something that is positively charged. So there was a few really interesting things that they were able to conclude as a result of this experiment. Firstly, their conclusion, because most particles actually passed through, was there was actually a lot of empty space. So lots of empty space. And the empty space suggests that alpha particles can pass straight through without being interfered in any way. Now, the existence of the other particles, most significantly this one, suggests that there was a highly concentrated positive charge in the middle. Positive charge that is concentrated in the middle. And this was responsible for deflecting our alpha particle completely backwards. So that's roughly how they were able to achieve the current model for the structure of the atom, or to really prove or demonstrate that the center of the atom is really the way that it looks currently. Okay, so right now we're going to go look at a simulator. So this is available on Cognity, and I would encourage you guys to look at this simulator as well. So I'm going to turn on traces here, and then we're going to start this alpha particle beam. So if you look at the legend on the side, alpha particles is flowing through, right? We have the big pudding of positive charge in the middle, with the electrons being scattered roughly evenly, making the entire thing neutral. So if the plum pudding model was true, all the alpha particles should more or less pass straight through because it's not affected by the neutrally charged atom inside. And we're going to go to the Rutherford model now. And I'm going to turn on traces as well, just so you can kind of see, maybe can I reset this? Yeah, okay. So I'm going to reset this. So if we look at these particles, you can see that the nucleus of the atom being so small allows for charged particles to pass through it, so lots of empty space, and um, occasionally um, the alpha particles could be deflected by the center of the nucleus itself, which is highly concentrated and positively charged. And on very, very rare occasions, you may see a complete rebounding of the particles. And that's where, again, they were able to conclude that, yep, okay, this is true. Okay, the structure of the atom is that the center is very concentrated. Okay, so thank you guys for watching this video. We will come back in for chapter 7.3.2 on the structure of matter. Thank you guys for watching. See you next time.